Hello everyone, my name is Stefano and today I will be talking about the state of charge estimation or SOC estimation in an electric bus lithium-ion battery system. Battery management systems or BMS are responsible for monitoring and protecting lithium-ion batteries. One of their most important jobs is estimating the battery's state of charge. Unlike a fuel tank in a gasoline vehicle, we cannot directly measure how much energy remains inside a battery. Instead, engineers must estimate it using sensors, battery models, and estimation algorithms. In this presentation, I will explain what a state of charge is, why it's difficult to estimate, the most common estimation methods, and how battery management systems use SOC to improve safety, performance, and battery life. Electric bus battery system. I chose an electric bus battery pack because public transportation depends on accurate battery information to complete daily routes safely and efficiently. Modern electric buses typically use lithium iron phosphate or LFP batteries or nickel manganese cobalt batteries known as NMC. These battery packs usually operate between 500 and 800 volts and have capabilities ranging from 300 to 700 kilowatt hours depending on the manufacturer and bus size. A state of charge estimation is extremely important because it allows the driver and the battery management system to estimate the remaining driving range, schedule charging, prevent overcharging and deep discharging, and extend the overall battery lifetime. What is a state of charge? A state of charge is simply the percentage of usable energy remaining inside the battery compared to its maximum available capacity. For example, a battery at 100% SOC is fully charged. At 50%, roughly half of the usable energy remains. At 0%, the battery is considered fully discharged. One important point in that state of charge is not the same as battery voltage. Many people assume voltage tells us exactly how full a battery is, but voltage also changes depending on temperature, battery age, and how much current the battery is delivering. Because of this, voltage alone cannot accurately determine the state of charge. Why SOC is difficult to estimate? Estimating a state of charge is challenging because it cannot be measured directly with a single sensor. First, battery voltage changes as the battery charges and discharges. Second, voltage also changes whenever the battery is supplying current. For example, when an electric bus accelerates, the battery voltage temporarily drops because of the heavy electrical load. Temperature is another major factor. Cold temperatures reduce battery performance, while high temperatures affect battery chemistry differently. Battery aging also changes the battery's capacity over time. As battery age, they cannot store as much energy as they were when they were brand new. In addition, the battery's internal resistance changes with age, which affects the terminal voltage. Finally, current and voltage sensors always contain some measurement noise. Because all of these factors influence battery behavior, engineers must estimate a state of charge using mathematical models instead of directly measuring it. Coulomb counting. The first estimation method is called Coulomb counting. This method measures the battery current continuously and calculates how much charge has entered or left the battery over time. To perform this calculation, the battery management system needs three main inputs: battery current, battery capacity, and an initial state of charge. One advantage of column counting is that it's simple, fast, and works continuously while the vehicle is operating. However, it has one important limitation. If the current sensor contains even a small error, those errors accumulate over time. This is called drift. And eventually the estimated state of charge becomes inaccurate unless another method is used to recalibrate it. Open circuit voltage method. The second method is called open circuit voltage or OCV method. Instead of measuring current, this method measures the battery voltage after the battery has rested long enough for the voltage to stabilize. The measured voltage is then compared to a reference curve that relates open circuit voltage to a state of charge. This method provides good long-term accuracy and is commonly used to recalibrate other estimation methods. However, it has one major disadvantage. An electric bus is usually driving throughout the day, so the battery rarely has enough time to rest. Because of this, the OCV method cannot provide continuous state of charge estimation while the vehicle is operating. Battery model. To improve accuracy, battery management systems use electrical models that represent the battery's behavior. One of the most common models is the Thevenin equivalent circuit model. In this model, the open circuit voltage represents the battery's ideal voltage source. The resistor, called R0, represents the battery's internal resistance and accounts for voltage losses when current flows. The RC network models the battery's transient behavior and voltage response over time. Using this model, the battery management system predicts what the battery voltage should be under different operating conditions. This predicted voltage is then compared with the actual measured voltage to improve the state of charge estimate. Extended Kalman filter. One of the most widely used estimation algorithms today is the extended Kalman filter, or EKF. The EKF combines the battery model with real-time current and voltage measurements. First, the algorithm predicts the battery's state of charge using the mathematical battery model. Next, it measures the actual battery voltage and current. Then it compares the predicted voltage with the measured voltage. If there is a difference, the algorithm automatically corrects the estimated state of charge. This prediction and correction process repeats continuously many times every second. The biggest advantage of the extended Kalman filters is that it reduces measurement noise and provides much more accurate state of charge estimates than simpler methods. For this reason, EKFs are widely used in modern electric vehicles and electric buses. SOC in the battery management system. State of charge estimation is one of the most important functions performed by the battery management system. First, it estimates the vehicle's remaining driving range so the drivers know how much farther they can travel. Second, it controls battery charging and prevents overcharging, which could damage the battery. Third, it prevents excessive battery discharge, helping avoid permanent battery degradation. The battery management system also manages battery temperature through thermal management. Another important function is cell balancing, which ensures every battery cell remains at a similar state of charge. Finally, the battery management system monitors battery health and limits available power whenever the battery becomes too low or too hot. Advantages and limitations. A state of charge estimation provides many important benefits. It improves battery safety by preventing overcharging and deep discharge. It provides more accurate driving range predictions, helping drivers plan their trips. It also extends battery life by ensuring the battery operates within safe limits. However, there are also some limitations. Sensor noise can reduce estimation accuracy. Battery aging changes battery characteristics over time. Temperature also affects battery performance. In addition, advanced estimation methods such as the extended Kalman filter require accurate battery models and greater computational power. In conclusion, accurately estimating a state of charge is one of the most important responsibilities of a battery management system. Because the state of charge cannot be measured directly, engineers rely on methods such as Coulomb counting, open circuit voltage measurements, battery models, and the extended Kalman filter. Together, these techniques help electric buses operate safely, improve range prediction, protect the battery, and maximize battery lifetime. Thank you.